Okay, so let's begin today's webinar, which will be focused mainly on LI-COR's new eddy covariance data processing software. I'm Israel Begashau. I'll get us started here, and my colleague Gerardo Frattini, who was one of the primary software engineers working on EddyPro, will walk us through most of the webinar. To just give you an overview of what we will be doing today, we'll do an overview of EddyPro Express software by running a processing session where we will use a data set that's collected in the TOB1 file format. We will then go into an explanation of the steps and routines EddyPro Express uses in computing fluxes and applying necessary corrections. Next, we will discuss how the new GHG software for LI-COR's new analyzers can significantly facilitate data processing in EddyPro. We will demonstrate this by running a processing session with a data set that has raw files in the LI-COR GHG format. We will also describe how you can set up your instrument so that you can collect data in the GHG format. Before we finish, we will take a look at the results of outputs from an EddyPro run. We'll discuss what those files include and what quality flags and fluxes we get, and also what the meaning of the quality flags are. So these are the items that we intend to cover in this webinar. It's a long list of items, so we cannot go in detail on every aspect of the software, but we will highlight the important aspects, and we will guide you to the help system available for EddyPro. EddyPro has a help system in PDF and online format. The online format also includes video tutorials on how to run processing sessions for different file types. So I will encourage you to go to those in case you have questions. At this point, I would like to pass it off to Gerardo so he can walk us through EddyPro.
Thanks, Israel. Let's launch our first poll before we turn the floor over to Gerardo. How much do you know about eddy covariance method? Your answer choices are: I have only heard about it, I am familiar but not using it, I know about it and am collecting data, I know about it and am collecting and processing data, I consider myself an expert. Go ahead and click the radio button next to your answer choice. We will give everyone a few moments to respond. Alright, I'm going to close the poll now. Thank you for your responses. Here are the results. It looks like we have a pretty diverse mix amongst the group. Thank you. Gerardo, let's get back to the presentation.
Thank you, Angela. Thank you, Israel, for the presentation. Hello, everyone, and welcome to this meeting, to this webinar. So I'm going to introduce you to how to run processing sessions using EddyPro to get your fluxes out of your raw data. And I'm going to also show you a little bit about what EddyPro does to process data and to calculate and correct fluxes. Before starting, anyway, I would like to introduce you to a little bit of the history of EddyPro, how it started and where it's coming from. I will start speaking about ECOTUS. ECOTUS stands for Eddy Covariance Community Software. This is a free and open source eddy covariance processing software that was developed and was released a few months ago by the consortium that participated the European project IMEC, and was developed mainly in Italy at the University of Tuscia. But in fact, as the name says, it was mostly a community effort where many scientists contributed and provided corrections and routines, and also helped in validating the software. We had an extensive software intercomparison involving 6 other software packages. So LI-COR decided to start from ECOTUS and to build up a new product, and the result of this effort is EddyPro in its current release, that is EddyPro Express. EddyPro is also a free and open source software. We like it. We want you to go to the LI-COR's website, download it, and look at the source code, see how things are implemented, and feel confident about how we process data and how we get to the fluxes. However, EddyPro Express is radically different from EcoTools in that it focuses mostly on the ease of use. So it features a predefined yet very accurate data processing and flux calculation and correction. As Israel introduced, we also have an extensive documentation with video tutorials and contextual help that will help a lot in configuring the software and understanding the results. Okay, we are speaking about the software, so I would rather take away this PowerPoint and go and open software, play with it a little bit. Let's first familiarize with the dataset we are going to process. In this folder, we have 3 subfolders. Each subfolder has raw files, 48 raw files, 30 minutes long, so we have 1 day of data in each folder. They all refer to the same period, so the same day, but they are in different formats. Okay, that's our raw dataset. And now I'm going to open EddyPro. I will click on the icon that I find on the desktop after installation. And I will enter in the start page of EddyPro. Here you can see 2 buttons, Express and Advanced. Advanced is not yet active, but watch out for the release of Advanced. It's going to be a nice tool to you as well. So let's select Express and enter the software. So we have we enter in the project page here, and then we have a processing page. In the project page, we enter information about our files, what's inside the raw files. We give information about our site and station and how data have been collected. This information are used by the software to process data correctly. In the processing page, we select the actual dataset that we want to process. We make a little bit of choices, and we select the variables that we want to use for calculating the fluxes. Okay, I'm not going to give you all the details about how to fill out all the information here in the graphical interface. It's quite intuitive, and anyway you can access the help. You have a local copy in PDF, and you have a remote copy on LI-COR's website that you can access from the help menu. I'm just going to enter the most relevant information. So let's start by giving a name to our processing project. I will call it something like webinar. Well, webinar. Okay, that's enough. And next step is to select the format of the raw files that we want to process. We have 3 options, LI-COR GHG. We will speak about it later. ASCII table. This file type includes virtually any sort of text file, organized in data columns. And TOB1. This is the binary format of the files that you get from Campbell Scientific Data Loggers. Well, I know that most of you probably don't have LI-COR GHG files because this is a relatively new data format. So I'm going to show you how to run a session with TOB1 files. And just keep in mind that to process ASCII files, you will have to follow approximately the same procedure. So I'm selecting TOB1. And as soon as I do that, this part activates. This is the metadata file editor. Here we enter the information about the site, the session setup, the instruments that we used for collecting data, and we describe the content of the raw files. All this information will be stored in a file that we call metadata file. So you can save this file, and I'm going to do this as a first step. So save metadata as. I will browse to my TOB1 folder where I have the files in TOB1 format and give it a name like TOB1. The extension of this file is going to be metadata, quite intuitive. Once you have created a file and you have edited that, you can always load it when you know, for the next session, you can always load it from this button here. I will show you later. Okay, now we have to enter the information about our site and station. For convenience, I collected this information in a slide that I'm going to show you now. This is the slide. We have information about the site. This is our landfill site here in Lincoln. We have the geographic location, the canopy height, the instruments used. We have a Gilwin Master Pro anemometer. We have 2 gas analyzers, LI-7500A for CO2 and water vapor, and LI-7700 for methane. We have the measurement height, 3.3 meters, acquisition frequency 10 Hz, and file duration is 30 minutes. Then we have some setup, like the distances of the instruments with respect to the anemometer. So we have the 2 gas analyzers, and northward and eastward distances with respect to the anemometer taken as a reference. And then we have the settings of the anemometer, the wind configuration, how the wind vector is given in the raw files, the configuration where the U component of the wind vector is pointing, in this case our north spar, and the north offset of our sonic, that is 42 degrees. And also, when we collected the data, we didn't have the head correction applied in the inside the sonic, so we will keep this in mind. So let's go back to the graphical interface, and let's fill this information. We have file duration 30 minutes, 10 Hz acquisition frequency. We have an altitude of 358 meters, and a canopy height of just 5 centimeters. We have just sparse and short vegetation over there. Okay, here I should enter the displacement height and the roughness length. If you don't know what these are, you can just leave them 0 and the software will take care of it. You can learn more about them by clicking on the question mark here. Probably I should mention that the green field you must enter, while the blue ones are optional. So I'm just going ahead and leave them at 0. Let's see what happens. Okay, so now I enter the latitude of our site. It's going to be 42 and 48 degrees north, and the longitude, that is 96, I believe, 0.40 west. So I'm going to write W here. Okay, now let's move to the instrument section, and let's describe our anemometers and gas analyzers. We have 1 GIL anemometer. It is a Wind Master Pro. Here you can see all the models that we support. I'm not going to enter the serial number or the ID. They are not needed for flux computation. The measurement height is 3.2 meters. The wind vector is coming as U, V, and W, as opposed to polar and W or axis velocities. The north alignment is spar, as we have seen. And we have a 42 degrees offset with respect to true north. This is important for the wind direction, And okay, then we have the head correction. We just say it is not applied, and so I will enter no. If you have a second anemometer, you can click on plus here and fill out all the information for that one, but we don't have it, so I will click on minus and take it away. Okay, let's fill out now the information about the gas analyzers. We have 2 analyzers, so I will click already on plus, and let's describe them. We have an LI-7500A, and these are all the others that we support, and we have an LI-7700. Both are placed at 3.2 meters above the ground level. And okay, here we have tube length, inner diameter, flow rate. Of course, this information apply to closed path analyzers for which you have an intake tube. We don't have it in our 2 open path analyzers, so I'm just going to ignore these entries, and I will enter here the 20 centimeters north separation for both instruments, the 15 centimeter east separation for the LI-7500A, and the 15 centimeter westward separation, so I'm going to enter -15 eastward. Israel later will tell you a little more about these separations. Okay, here we are done. We can go to the raw file description. Here we describe the raw files. So let's first have a look at how our raw files look like. Okay, I'm going to just pick one, say the first, open it in Excel. Of course, TOB1 files are binary. We can't read the data, but we can read the header, and that's all we need. Let me just format it in a slightly better way. Here we go. In the second row here, we have all the variables present in the file. Let's see how many they are. Okay, they are 23. So we have 23 variables. Let's have a look. What do we have inside? We have 5 initial columns that we don't really need for flux computation. Then we have CO2 and water vapor number density expressed as millimole per cubic meter. We have air temperature and pressure measured by the LI-7500A. We have the wind components, the starting temperature, a couple of readings more for CO2 and H2O, and the AGC diagnostic value. Following, we have all the measurement for from the LI-7700 for methane. We have the methane concentration and molar density. We have again temperature and pressure, and some diagnostic values here. Okay, let's enter this information here in the graphical interface. We have 23 variables, so we need 23 columns to describe all of them. I'm going to enter here quickly, click on the plus, 23 columns. Here we go, we have 23 columns, and let's start to fill them out. I just say that we don't need the first columns for calculating the fluxes, so I will instruct EddyPro to ignore those columns just by selecting the variable name ignore. This is going to be true for the first 5 columns, referring to the first 5 variables. Okay, then 6 and 7, let's go back to the file just to make sure. The 5th and 6th, well, 6 and 7 actually, we have CO2 and water vapor. Okay, so I'm going to enter CO2 concentration and water vapor. Okay, we know that they are measured by the LI-7500A, both of them. They are measured as molar densities and in units of millimole per cubic meter. Okay, well, I believe you don't want to see look at me filling out all the 23 columns, huh? So I'm going to stop this and I will take a shortcut. I prepared a metadata file before this webinar, and I'm going to load that file from here, as I told you before. So we will overwrite what we just typed, but we will be faster. Here it is, TOB1 precompiled metadata. Here we are. All the information are inside for all the 23 columns. We have the methane and the wind component, starting temperature, and everything. Just let me show you quickly that which are the variables we can enter. We have wind components, starting temperature, speed of sound, gas concentration, cell temperature and pressure for closed path analyzers, ambient temperature and pressure, diagnostic flags. These are used for flagging individual raw data. Okay, and then we have a couple of ignore labels. Good. Last thing we have to do here in the project page before going to the processing page is to enter the raw file name format. The raw file name format is a template that the software uses to retrieve timestamp information from the names of the raw files. So the easiest way to enter this is to copy the name of a raw file on your clipboard, go back here and paste it. Okay, so here we have the name of a file. Now we will replace the timestamp information with some predefined codes that will instruct EddyPro to retrieve the year. You have put 4 times Y, the month 2 times M, and the day 2 times D. Here we have 5 o'clock, so it's going to be capital H 2 times and capital M 2 times. Okay, so with this template, EddyPro will be able to interpret all raw file names and retrieve the timestamp. Well, if you are in trouble understanding this, you may click on the question mark again. Well, let's try and do it. Okay, what happens is that the browser opens, and if the internet is fast enough, you get to the raw file name contextual help. Oh, in this case, we also have a nice video tutorial that you can look at to learn how to enter correctly the raw file name format. Okay, so let's close here, and let's move to the processing page. Okay, in the upper part of the processing page, we enter information about which data we want to process. So I'm going to select the raw data directory by clicking on Browse. We are processing TOB1 files. You don't have to select the files, just enter in the folder where the files are. Okay, and then I select the output directory. Actually, I create a subfolder inside our raw data folder, and I call it kind of results. Seems good. Okay, and finally I enter an output ID. This is a string that is going to be attached to all results files, for distinguishing them from previous runs or future runs. Okay, here you just have to enter the initial date and final date of the data set you want to process, and the flux average interval. But let's look here, it's more interesting. The software was able to recognize from the metadata that we entered before that we have a Windmaster Pro here. We have CO2, water vapor, and methane readings from our instruments, and we have a couple of ambient temperature from both instruments, and you can pick the one you prefer. I'm going to choose the one from LI-7700, and the same is true for pressure. Last step is to save this processing file, processing project, so that you can open it in the future at any time, and you will have all the settings popping up on the graphical interface. So I save it inside the TOB1 folder. Well, I already have one here. I will override it. Okay, we are done. We are ready. You can just click on Run and see the processing go through. It started. It's calculating the fluxes, and we have a scroll bar here that will give you an idea of how long is missing until the end of the processing. And on the output console, you have some diagnostic information.
Gerardo, while the program is running, may I interrupt with an audience question?
Sure, go ahead.
How long does it take EddyPro to process 1 month or 1 year of data files?
Well, the answer depends on different factors. It depends, of course, on your computer, on the capabilities of your computer. It depends on the raw file size, how many columns are inside, and also on the format. Roughly, we can say that we can process 1 year of data in a time that is about from 4 to 12 hours approximately.
Thank you.
Okay, so while the processing goes through, I'm going to show you a little bit of just give me a second to load. Okay, here we are. I'm going to give you just an overview of how EddyPro processes data, how it handles the data and calculate fluxes and correct fluxes. Okay, so as a first operation, after importing the data, the software checks if you defined a diagnostic flag in your raw data. If you did, the software will eliminate all the records that correspond to flags, flag for poor quality. So at the end of this first step, you may find your data set a little bit shortened because some records have been eliminated for for quality assurance. And after that, we have the spiking procedure according to the method proposed by Vickers and Mart in the paper of 1997. You will find all the references at the end of this presentation, and you also have them in the help system of EddyPro. Okay, the 5 tests that we perform after a while. Okay, the first one checks the number of spikes for each variable, so it counts a spike with respect to the number of records and flag the file if you have too many spikes. The second test goes, it checks for the number of individual data values that are outside physically plausible ranges. Then we have a test for the amplitude resolution. This test basically tries to assess if the turbulent fluctuations in your time series are such that your instrument is not resolved enough doesn't have resolution enough to measure them properly. The fourth test, the dropouts, attempts to assess whether there are periods in which your time series sticks to a value that is far away from the average value in the time series. Okay, the last test checks some statistical properties of the time series, skewness and kurtosis. For these 5 tests, you will get flags in output, and we will see it later. After a while, depending on the model of the anemometer that you use to collect fluxes, raw data, the crosswind correction may or may not be applied. Also, the angle of attack correction for correcting the flow distortion induced by the anemometer frame on the flow field is applied for gill anemometers with the vertical mountings. After a while, the double rotation scheme is applied to compensate the anemometer tilting with respect to the local flow field. The double rotation nullifies the average crosswind and vertical wind components. As a last, not really, is the 6th step. We calculate the turbulent fluctuations by eliminating the block average calculated on the full time on the whole time series. And as a last step, the 7th step, we compensate the time lags of the scalar concentration with respect to the anemometer variables. So the time lag is first detected with a covariance maximization procedure, and then it's compensated. At each of these 7 steps, EddyPro measures, calculates statistics such as mean values, standard deviation, variances, covariances, skewness, and kurtosis, and will provide them in output. Using the last level of statistics, so the 7th, it will calculate a first flux estimate. You will have these uncorrected fluxes in your output files, but you don't want to use these fluxes for your further analysis. These fluxes must be corrected, and that's what the software does after a while. There are several corrections involved. There is the air density fluctuations, the so-called WPL correction or WPL term, the off-season uptake correction for the LI-7500. We have the spectroscopic correction for the LI-7700. Of course, we have the spectral correction for the attenuation of the co-spectra at both the high frequency and low frequency ranges, and the sensible heat correction for humidity. Some of these things may not tell you much, but you will find description of them in the documentation, and you will have in the software documentation you will have links to the papers to read more about them. Well, these corrections from 10 to 14 are not necessarily applied in this order. It depends on which instruments are used. If you have open path analyzers, closed path analyzers, just to say one, if you have only open path analyzers, the spectral correction is applied before applying the WPL correction. The other way around, if you have only closed path analyzers, the WPL is applied first, and then the spectral correction is applied. In some cases, an iteration of the correction might be needed, and it's applied. All this, the pattern that is followed by the software to process the data depends, again, on the metadata that you entered, and the software will just decide according to what you entered. You will not have to choose anything about it. Okay, so along with the fluxes, we also provide some further parameters, useful parameters. We have meteorological values for dew point, temperature, relative humidity, water vapor pressure, VPD, and several others. We have turbulence parameters, so wind speed, wind direction, friction velocity, stability parameter, scaling temperature. And there is a footprint parameterization in EddyPro that will provide you with an estimation of the flux footprint. You will have three numbers. The peak contribution distance will tell you which is the distance from the tower that contributes the most to the fluxes. And then you have the 70% and the 90% contribution distances. We will see them later also in the output files. Finally, the software applies true quality tests, true micrometeorological tests, and combine the results to provide you with a flag that is attached to all the calculated fluxes. Okay, here we have all the references that I cited. You will find more in the documentation.
All right, Gerardo, before you move ahead, let's do our second poll question. What do you find most challenging about processing eddy covariance data? I don't know what correction steps I need to apply, mathematical complexity of the corrections and functions, programming difficulty dealing with large data sets and variables, lack of easy-to-use software programs for processing, lack of clear documentation and support for existing software. Please click the radio button next to your answer choice. We will give everyone a few moments to respond. Alright, I'm going to close the poll now. Thank you for your responses. Here are the results. Thank you. Gerardo, let's get back to the presentation.
Okay. Yes, well, before we go on with the presentation, let me just comment on these results. Well, it seems that most of you find eddy covariance a complex topic, and it's difficult to understand exactly what to apply and how to apply. And, well, also, the lack of easy to use software seems to be an issue. In fact, all these things are rather true. Eddy covariance is complex, and what we are trying to do at LI-COR is to get you free from this complexity and take charge of it. We want to deal with this complexity. We want to provide you a system that is as easy as possible to use, and this includes providing you a software that is easy to use. But we also went a little further. We designed a new file type that Israel introduced shortly before. This file type that we call GHG, it's revolutionary in a way because it bundles the meta information that we need to calculate the fluxes and to decide how to compute the fluxes with the raw data. So just Israel will tell you more about it later, but just let me show you here in the GHG folder. Each of these GHG file is a ref file that bundles high frequency data and meta information. So I'm going to show you now how easy it is to process these files using EddyPro. You might be wondering how you can collect these GHG files. If you have the LI-7550 instrument interface with the latest release of the GHG software package, you will be able to collect GHG files as Israel will show you later in details. Okay, so now I'm going back to the software. I could click here on new project and start from a blank page, but to make you feel confident that there is nothing I entered, I will just close the software and open it again to run a processing session with the GHG files. Okay, let's click again on Express. let's give our project a name. I call it GHG this time. Well, processing. I select the raw file format LI-COR GHG, and I select the option Use Embedded Metadata, means embedded in the raw files. So that's all. We don't have to do anything else here. All the meta information we entered before for the TOB1 files, we don't have to enter. They are inside the raw files. We can just go to the processing page. We instruct the software to find our files in the GHG folder. We select an output folder. I will create also here a folder called results and select that one. I enter an output ID. You see here that as soon as I entered the raw data directory, the software was able to populate all these entries because it went to look inside one of the GHG files and retrieve the same meta information that before I had to enter explicitly. So that's it. Everything is filled out. I can just save my project. I will overwrite this existing file and click on Run to start processing my GHG files. It took less than 2 minutes to configure and start the running of the software with the GHG files. And now I will pass it over to Israel, who will show you how is it possible and how we got to arrive at this point. Thank you.
Thank you, Gerardo. While Israel is taking his place, I'd like to let our audience know that the EddyPro software can be downloaded from the LI-COR environmental website for free. Visit www.licor.com/env for more information. Israel, are you ready?
Yes, Angela. All right, so let's see how and why Gerardo was able to get to the run very quickly with the GHG format. So what does the GHG format include? Let's see here if we can load up the presentation. So LI-COR recently released the software update for the LI-7550 analyzer interface unit. This analyzer interface unit and its update brings in the option of compressing the high frequency data and the site and station information into a single archived file that is collected on a USB drive on the analyzer interface unit. The compressed file has a .ghg extension, so all the raw files that you will collect will have this .ghg extension. And it can be set up, to contain all the information EddyPro requires for processing data and computing fluxes. EddyPro Express uses the metadata and makes a decision on how it should correct or process your high-frequency data and apply the necessary corrections. This software update is compatible with LI-COR's new gas analyzers, namely the LI-7500A Open Path Analyzer, the LI-7200 Closed Path CO2 H2O Analyzer, and the LI-7700 the Open Path Methane Analyzer. So this is the archived file that we're talking about. So let's go ahead and go to the folder where Gerardo saved his sample data files and see what is inside this archive. So this .ghg, like any other archive, I can use a utility like 7-zip to extract. So I'll click on extract and do here. So it created a folder with the same file name as the .ghg file, but it's instead of just being one file, when I go into that folder, I see two files. As you can see, there's a data file with a .data extension and a .metadata extension here. As if you remember, when Gerardo was processing TOB1 files, he saved this metadata file. What we've done with the GHG format is already, while you're at the station, we give you the opportunity to create this metadata, and we compile it and put it together with the high frequency data and make it into one file. In this file, in the metadata, you have your site information and station information, instrument setup, and so on. And in the other file, you have your gas concentration, your UVW, your temperature and pressure, high frequency measurements. All right, so where in the instrument software do we enter this information? How can we get to that? So I'm just gonna get out of this presentation here. EddyPro seems to have finished, so I'll say OK here and open the instrument software for the LI-7550. This LI-7550 instrument software version is number 5.0.0. So I have a few instruments set up that I'll connect to. I call it webinar instruments. So as you can see, we have data coming in from the instrument. We have it's a 7500A open path analyzer. We have CO2 and water data and temperature and pressure here. This software allows you to talk to your instrument and configure it, enter the calibrations and so on. There are different tabs up here. Inputs is where you set up your sonic inputs and the analog inputs. Outputs is for if you're using RS-232 or other. But for our purpose, where we set up the metadata and where we set up the logging is here in this logging tab. So if you click on the logging tab, you have different options. The instrument USB tab is the first one, and the PC logging is the second one. For the USB tab, you have the first choice is the update rate or the collection rate. So how frequently are you collecting data? So we're going to save it, stay at 10 Hertz. File duration, each file will be 30 minutes long. And compress files. This compress files is what allows the instrument to write the GHG. In addition, this compression also saves a lot of space on the USB drive, so that you can, that 4 GB that usually comes with these new instruments can last you a very long time. And then you have other options where you have decide what to do after when the data gets filled. You have also other options to split duration and, for collection 10 or 20 Hertz and so on. But the most important part for making it easy to process data with EddyPro quickly is this log site information or .metadata. So I'm going to go to this update site info page, and I'm going to show you how the data that Gerardo processed is collected. So in this site information page, we have a similar structure to the structure that you saw in EddyPro. We have a tab for site information. We have a tab for anemometer information. We have a tab for gas analyzer information. So for the site information, we have site name and station name, altitude, and at the site, and canopy height, and also the displacement and roughness length. These, as you can see, are optional. And also we have the geographic location information here. We can enter it in a few different formats. For the anemometer page, we have a GIL Master Pro that Gerardo was working with. You have several other models that you can choose depending on what you have at your site. We'll just keep with the GIL and the WinMaster Pro. For the WinMaster Pro model, we have alignment options, North Star and transducer axis. And the data comes in these formats. So this is similar to what you saw in EddyPro interface. For gas analyzers, we have a CO2 analyzer, the open path LI-7500A. We have the option to choose 7200. If we chose the 7200, you'll see that tube length and tube diameter become enabled, and the values default to the standard tubing we provide with the instrument. If you change the standard tubing, you can enter that here. But we have a 7500A, so I'll click that, and you see that tube length and diameter option become grayed out. So the height is, like Gerardo did, 3.2 3.2 here again for the 7700. And we have some separation parameters that we need to enter. The separation parameters are measured when you're at the site after you set up your instrument, so that you can see, you can correct your wind and time lag information based on this. So let me show you how you can measure those, or at least what those values represents. Obviously, the vertical separation represents any separation between the midpoint of the sampling volume of the analyzer versus the midpoint of the sampling volume of a sonic anemometer, your reference sonic anemometer. And eastward and northward separation refer to separation in the east and west axis and the north and west axis. Okay. So let's go back to the instrument software where we're entering all this information. So we've done through this. We click apply, click OK. We get back to this main page where we have this set up. So we also get to choose the variables that we log. For example, we have time, date, and so on in this list. And we also have a 7700 connected, so we have variables from the methane analyzer. The bare minimum that you need are the density for water and CO2, temperature, pressure, diagnostics, and the auxiliary inputs where sonic data is coming. Similarly, you need density, temperature, pressure, and diagnostic information from the methane analyzer. But if you have space to add more, you can add absorbance for CO2 and water vapor to help you recalculate data for any erroneous calibrations and so on. After selecting the data that you want, you could click apply here, and that settings takes place. So to start logging, if you have a USB drive connected to your LI-7550 interface unit, you can click start here. Or if you don't have a USB drive and you've done this setup, as soon as you enter a USB drive into the port, data logging begins. So I can click start. It's going to start buffering data, and it's going to start collecting data. When data is being collected, at the end of every half hour, the high frequency data and the information we entered about our site is going to be bundled together, and that data is going to be compressed into a GHG file. I'm going to disconnect from this instrument and close here and get back to the presentation here. Let me just highlight some of the benefits you get from a GHG file format. The GHG file format allows you to store several weeks of data on a single 4 GB USB drive that we send with the new analyzer packages. You can achieve up to a 10x compression. As Gerardo showed us, it significantly simplifies data processing using EddyPro. In addition, it allows you to automatically account for any changing site parameters. For example, if the instruments on the tower are raised to a new height because of canopy growth, while you're at the site and raising the instruments, you can go into the software that I just showed you and update the information. When you update that information, it gets embedded again with the next set of GHG files that you collect. When you process, you don't have to do anything to account for those changes because all that change is already embedded in the raw data file. The GHG file format is also a very prudent way to store raw data, since site information is included in the raw data. Years from now, the same data set can be easily processed by someone who may not be familiar with the initial setup. I'll stop here for now and ask Gerardo to show us what results we get from EddyPro and how we should interpret them.
Israel, before you move, may I ask an audience question?
Sure, go ahead, Angela.
I have the LI-7500 OpenPath Analyzer. Can I get GHG files?
The LI-COR GHG file format is created by the new analyzer interface unit, the LI-7550. It's a revamped and a very capable interface box compared to the old 7500 box. This interface unit is used by analyzer models LI-7500A, LI-7200, and LI-7700. The original model of the OpenPath analyzer, however, can be upgraded so that it can work with the new analyzer interface. This upgrade also allows you to collect data on the USB in the file format we discussed, but also it provides you the optional benefits such as Ethernet connectivity to your gas analyzer. All right, I'll let Gerardo take over.
Thank you, Israel. While Gerardo is taking his seat, I'd like to inform our audience that this session is being recorded and will be available for viewing in a few days. Please visit www.LI-COR.com/env/webinars to watch the replay. Gerardo?
Okay, thank you, Angela, again. So, as Israel said, we're going to look a little bit at the files, at the results files that we have obtained from our runs. We ran the software 2 times on GHG files and TOB1 files. I'm going to show you results for the TOB1 files. It's basically the same. Okay, in the main result folder that we selected, we have a bunch of files here. And then we have 2 subfolders, the stats folder and the user stats folder. Okay, all these files are formatted in CSV format, so they are comma-separated values. It's a text format that you can easily read and import with any post-processing software, such as Excel or MATLAB or whatever. Okay, in the stats folder, we have the 7 level of statistics that we discussed before. And I'm going to show you how one of these files looks like. They are, of course, all the same format. So let's go ahead and open the 7th level. Okay, we have a first line header. Here we see which procedures, which operations have been performed on the dataset, on the time series, before calculating these statistics. In the second row, you have the labels, and then you get results for each averaging interval. The first column gives you the file name, and second and third the timestamp. You may note that the timestamp here, 5:30, looks different from this. Actually, is different from the 5 o'clock that is here. This is because the file name here refers to the beginning of the averaging period, while EddyPro outputs all results in all cases with the timestamp of the end of the averaging period, and that's why you have this 30 minutes offset. Then we have the number of samples used for calculating the statistics in this for each file, and then you start with the values. So you have mean values for all variables. Of course, for the variables that are not available in the raw files, you get a not available label like this one, and then you get here mean values for wind components, sonic temperature, gas concentration, and air temperature, pressure, and so forth. The wind direction here, and then we start with the variances for the same variables. We have the covariances between all pairs of variables, well, at least the most relevant ones, and standard deviations, the skewness, and the kurtosis. Okay, so you get these results for each file at 7 levels. In the other folder, I'm not going to show you the files, it's exactly the same format, but you get the results, the same results, for variables that are in the raw file, but have not been used or selected for calculating the fluxes. Okay, so let's go now to look at what we have in the main output folder. We have this rich output file that contains virtually all that EddyPro calculates. We have 2 other files here, Ameriflux and GHG Europe. These 2 files contain just a subset of the most important parameters, so the fluxes, the quality flags, the gas concentrations and wind components, and so forth, already formatted in such a way that you can directly submit these files to the Ameriflux and to the GHG Europe databases. Okay, then we have the metadata file that contain all the metadata used for each file. We have a log file. Let's just open it quickly. This contains all the operations that the software did while processing the data, and you don't need to look at that. It's just for diagnostic purposes. Okay, so let's go and have a look at how the rich output file looks like. We have a first line of the header with a label for groups of results. Like here we have corrected fluxes and quality flags that group all the variables up to here. Then we have the second row giving us the labels, and the third row giving us the units. Again, we have the file name in the first column. We have the timestamp, date and time in the second and third, the number of records in the file and the number of valid records in the file. They may differ, of course. And then we have the corrected fluxes, so our high quality fluxes. We have the momentum flux, sensible heat, latent heat, and the gas fluxes, CO2, water vapor, and methane. Let's just plot quickly one of them, just to see how they look like. Here we have a daily course of sensible heat, latent heat, CO2. Well, this is I told you is our landfill site, so we have CO2 emissions that are actually normally well correlated with methane fluxes. Let's see if it's true. I'm going to put both fluxes together. Yeah, here we are. We normally observe this. We have this strong correlation between CO2 and methane emission from our landfill site. And okay, so let's take away the graph and go back to the file. You see several -9999 here scattered around. It looks like something going wrong. What happens in fact is that EddyPro provides you this error code whenever something couldn't be calculated for any reason. In this case, some conditions were such that the quality flag could not be calculated. Yeah, maybe I should mention that these are the quality flags, of course. So these columns close to the fluxes are the quality flags. Normally, the quality flags besides the -999 gets a value 0 for high quality fluxes that you can use for any kind of scientific analysis. Fluxes flagged as 1 are kind of a average quality, and we would suggest to use them for annual budget and ensemble analysis, but maybe not for too much detailed investigations. And the fluxes flagged with 2 are poor quality that you may want to discard. Okay, then let's go further. We have the storage terms, storage fluxes. Of course, we also here we have -99. This is because for the first file we don't have a previous file to calculate the time gradient of the concentration, so we cannot calculate storage for the first file, and that's why we get this -99 here. Then we have the gas concentration and densities. Let's look at the CO2. Then we have also water vapor and methane. We have molar densities, mole fraction, dry mole fraction or mixing ratio, and we have the time lag that has been detected and used to compensate, to align the CO2 with the wind measurements. Okay, so then water vapor and methane. We can go further. We have air properties. I will not bore you with all the names here. We have air temperature, pressure, density, heat capacity, and so forth. All these labels better than I don't know them. And we have unrotated wind components. So the wind components before the double rotation scheme. These are the ones basically measured by the anemometer after the angle of attack correction, if it was applied. And the rotated ones. As I told you before, the rotation scheme nullifies the average V and W components of the wind vector, and so you will have the wind speed here in the U component. Again, with the wind direction here. There is some redundancies in between the different files. This is because we think it's useful to have some kind of parameters and results bundled together for making scatter plots or this kind of analysis. Okay, the rotation angles here, the turbulence parameters, friction velocity, stability parameter, and dynamic temperature. footprint estimates, so the peak value in the 70 and 90% contribution distances. Again, we find this bunch of -9999. This is because the footprint model is only defined, our footprint model, for U star values, friction velocity values above 0.2. And that's why here you get this -99 for these values of U star less than 0.2. Then we have the uncorrected fluxes. These are the fluxes before the WPL, the spectral correction, the off-season uptake correction, and so forth. These are here mostly for example, because you may use them for evaluating the effect of these corrections, how they change the uncorrected toward the corrected fluxes. Here you have the spectral correction factors for each flux. SCF stands for spectral correction factor. It's a pure number. And here we go with some diagnostics. We have the number of spikes detected for each variable, of course for each file. And we have the results of the 5 tests. We have the spike, amplitude, resolution, dropout, and so forth. For each test, you have a flag. Each digit here is a flag. For each variable, you see U, V, W, sonic temperature, and the gases. So the first one refers to U. The last one refers to N2O. We don't have N2O in our files, so that's why we get a 9 here. That means the test was not applied. When the test has passed, we get a 0, so it's a good sign. And when the test doesn't go through, we get a 1. Like, for example, we get some 1s here for some for the skewness and kurtosis of some variables. Okay, we're almost done. We get again some variances and covariances. Just for your convenience, you don't have to go and retrieve them from the statistics files. And finally, we have the average values of the variables that were in the raw files but have not been used for calculating the fluxes. Okay, it seems all. I think that's all on my side, and we can proceed further.
Thank you, Gerardo. This looks like a good place for our last poll. Let's launch it while you are trading places with Israel. If you or your group processes raw eddy covariance data, what program tool do you use? EddyRe, ECPack, AltEddy, TK2 or TK3, or a self-developed program like MATLAB? Please click the radio button next to your answer choice. We will give everyone a few moments to respond. Okay, thank you for your responses. Here are the results. Israel, would you like to comment?
Sure, it's very interesting to see. We saw similar results in the morning too. Most people were using EddyRe or other self-developed program, whether it be MATLAB or a Fortran code they use to process their fluxes. That is kind of what we expected we would see, and we did some comparison of EddyPro Express performance against EddyRe and MATLAB. So let me talk a little bit about that and we'll conclude today's webinar. So over here we have some data where the data came from a wetland in Florida, and we did a comparison with an EddyRe routine and a MATLAB code written here. LI-COR, we did this comparison. As you can see, the fluxes for CO2 here presented trend very well together. And in fact, if we see a one-to-one comparison, we get good correlation between EddyPro Express results and EddyRe and EddyPro Express results and MATLAB. And this is done before frequency corrections for CO2. We also did the same type of comparison for methane flux. This methane flux comes from the landfill site Gerardo talked about here in Lincoln. We have, again, eddy and MATLAB comparisons, and from the CO2 flux data, it looks very close to each other, and we can do a one-to-one plot, which will show us that we have a very good correlation between agreement between the two results. Okay, so I just would like to summarize what we've covered in this webinar, and we will be concluding in the next few minutes. So far we've seen that EddyPro Express uses metadata information on the site and an instrument setup to decide on how the data, the high frequency data, can be processed, how which correction needs to be applied in what order, and so on. We also saw that the outputs contain several quality control flags that we can interpret and use for analyzing our fluxes and deciding on which ones to use, which ones to discard, and so on. In addition, we looked at how the new LI-COR GHG instrument software functions. We looked at how you can collect data by setting up your analyzer interface unit, the LI-7550, properly to log data and metadata together and compress it in the GHG format. And we also saw how by doing that you can significantly improve the post-processing section in your software, in your data processing routine. I would just like to point out that the next webinar will go into an in-depth look at the theory of data analysis. It will be coming up in June. The exact dates will be announced via email. Our first two webinars that we've done are on the website, as Angela has mentioned before. This one will also be on our website in a few days. We also would like to show you some resources that are available. As we talked today, EddyPro is on our website. You can download it for free and try it out. We encourage you to do it. We would like to get the feedback. Hope it will help you and hope you'll find it useful. We also have eddy covariance training here at LI-COR. It's a 3-day course that delves into the theory, design, implementation, hands-on installation of instruments for using the eddy covariance method. We also spend a day doing data processing and corrections and quality assurance, just like the webinar we talked about today. We will do several examples. You can register for the class on our website on the eddy covariance pages. We also have additional resources, dedicated application page, the newly published book on eddy covariance, a brief practical guide, which is also available for download freely, or it can also be ordered as a paper copy. So that's what I have for today, and I'll take a moment here to take some questions from the audience.
Thank you, Israel. We have just one question that we're going to ask you that came up during the presentation. Can we alter metadata and reprocess the data?
Sure, I'll try to answer that. Yes, that is possible. In fact, the GHG software allows you to do just that. As I mentioned during the presentation, if something changed at your site, your canopy height changed, or you added a new instrument even. So now you didn't have a methane analyzer, maybe because funding didn't come through, you weren't able to purchase. When you add that instrument to the tower, you can set up your GHG software to include that data, and that metadata will be added to the raw data file. So EddyPro will keep looking into that metadata to process your data. If you don't have GHG, you can still do the same thing. Once you create a metadata using EddyPro Express interface, you can create multiple copies of that, as many as you need, and use those to calculate or to process the subsets of data with the corresponding metadata files. All right. it's been quite an hour, an exciting hour to spend with you guys. We hope you enjoyed it. And I'm signing off and passing it off to Angela. Thanks, Angela.
Thanks for your questions. Thanks, Israel. Thanks, Gerardo.